Welcome to the Deep Dive. If you need a shortcut to being well-informed, well, you've definitely come to the right place. Today we're digging into a really fascinating story. It's about how a long-standing chemical puzzle involving the biggest planets right here in our solar system, Jupiter and Saturn, was solved. And the key, unbelievably, came from this really ancient, kind of weird object 50 light years away. Its nickname, the accident.
Yeah, it sounds simple on the surface, but this problem has really stumped planetary scientists for decades. It all comes down to silicon. It's one of those common elements out there, makes up something like 9% of all cosmic dust. You'd think it would be everywhere. But when we look closely at the atmospheres of Jupiter, Saturn, and honestly thousands of other gas giants and these things called brown dwarfs, the silicon was just gone, completely missing.
Right. The theories, the atmospheric models, they all insisted it had to be there in some form. But every time we looked, nothing. And now, finally, thanks to some new findings published using the James Webb Space Telescope, the JWST, we actually have the first real observational evidence to crack this thing open. JWST found a silicon-based molecule, it's called Silane, CH4, in the atmosphere of this accident object.
Exactly. And our mission today really is to unpack how that discovery connects directly to how incredibly old this object is, and crucially, how that age ties into the basic chemical makeup, the elemental mix of the really early universe. It turns out this one detection links the chemistry you see floating in a planet's atmosphere straight back to the cosmic era it was born in. It's quite profound, actually.
Okay, so let's start with the object itself, this cosmic relic that gave us the answer. The accident. It's a brown dwarf. So just to clarify for everyone, a brown dwarf is, well, it's kind of a cosmic in-betweener. Too big to be just a planet, but not quite massive enough to ignite nuclear fusion like a proper star. They're super interesting, though, because as they cool down over billions of years, their atmospheres start looking a lot like gas giant planets. They make perfect little cosmic labs for studying planetary atmospheres.
But the accident is weird, even for a brown dwarf. It shows this really confusing mix of features. Some look like they belong to a warm, young brown dwarf, others to a much cooler, older one. And that very strange signature, that spectral fingerprint, meant it completely slipped past the usual ways we find these things. The standard detection methods just missed it.
That's amazing. And wasn't it found, relatively recently by someone just looking through old data? I read it was a citizen scientist volunteer, Dan Castledon, back in 2020, just scanning data from NASA's old NEO-WISE mission for a project called Backyard Worlds. It kind of shows you sometimes you need fresh eyes on old information to find these hidden gems.
Absolutely. And those fresh eyes found something incredibly old. I mean, really old. Researchers estimate the accident formed somewhere between 10 and 12 billion years ago. Now remember, the universe itself is only about 14 billion years old. So this thing is one of the oldest brown dwarfs we know of. It's basically a fossil from the early universe. When it formed, the cosmos was mostly just hydrogen and helium. Very few of the heavier elements that we see around today had been created yet. It was a low metallicity environment, as we call it.
Okay, so if it's that old and presumably quite faint and strange, what were the challenges in actually getting a good look at its atmosphere? How did they even study its chemistry?
Well, yeah, it's incredibly faint. So the first step involved using powerful ground-based telescopes like Gemini South. But that was really just to figure out how long they'd need to stare at it, to estimate the exposure time needed for the big guns. To actually pick apart the light and get the detailed molecular fingerprints from its atmosphere, they absolutely needed JWST, NASA's James Webb Space Telescope. Its sensitivity, especially in the infrared, was basically the only tool powerful enough to do that kind of detailed spectroscopic analysis on such a faint, distant object.
And JWST delivered. It found the thing everyone was looking for, or maybe didn't know they were looking for in this exact way. Silane, CH4.
That's the one, Silane. It's a fairly simple molecule, structurally speaking, just one silicon atom bonded to 4 hydrogen atoms. But the implications are huge. This detection, it's a first, a genuine scientific record. It is the first confirmed detection of Silane in any brown dwarf, any exoplanet, or even anything in our own solar system, ever, period.
Wow, okay, so that immediately flips the script on the original mystery, doesn't it? If Silane was expected, theoretically, in places like Jupiter, why does it only pop up now, in this one, very specific, super old, kind of weird object? What's different about the accident?
And that brings us right to the core of it. This chemical competition, essentially, between oxygen and hydrogen fighting over the available silicon. So let's rewind back to our local giants, Jupiter and Saturn. They're relatively young, right? But 4.6 billion years old. And crucially, they formed in a chemical environment that was already pretty rich in heavier elements, especially oxygen, forged in earlier generations of stars.
Okay, so more oxygen around when Jupiter formed, and you're saying silicon prefers to bond with oxygen if it's available, forming heavier stuff.
Exactly. When there's plenty of oxygen, silicon preferentially links up with it. It forms silicon oxides. Think of these as basically tiny, tiny grains of rock. Microscopic bits of quartz, SiO2, things like that. They're dense.
Right, so Jupiter basically takes its silicon and locks it up into these little dense rocky particles. What happens to them then? Do they just float around?
No, they sink. This is the key mechanism, what the source is called chemical sequestration. Because these silicon oxide particles are dense, much denser than the surrounding hydrogen and helium atmosphere, they drop. They might help seed some high-altitude clouds initially, but on cooler gas giants like Jupiter and Saturn, they quickly sink deep, deep down, way below the cloud layers we can actually see, like the water vapor and ammonia clouds. So they become, as the researchers put it, effectively invisible, even to probes we've sent there, like Galileo or Juno. The silicon wasn't actually missing, it was just hidden deep inside.
Ah, okay. So Jupiter and Saturn hide their silicon by basically turning it into rocks that sink out of sight. How did the accident avoid this? What happened differently back when it formed 10 or 12 billion years ago?
The difference is history, cosmic history. When the accident was born, the universe was fundamentally different chemically. Stars hadn't had nearly as much time to cook up heavier elements through fusion and supernovae, so the gas cloud it formed from had a much, much smaller supply of those heavy elements. And critically for this story, far less oxygen was available compared to when our solar system formed billions of years later.
Okay, so not enough oxygen around back then to use your term. Gobble up all the silicon.
Precisely. There just wasn't enough oxygen to bind with all the available silicon atoms.
So what did the silicon do instead? What else could it bond with?
Well, what was the most abundant thing around by far? Hydrogen. The universe was almost entirely hydrogen and helium back then. So with oxygen being scarce, the silicon was essentially forced to bond with the overwhelming abundance of hydrogen atoms. And that chemical pathway leads directly to the formation of Silane, CH4.
And Silane, CH4, unlike those heavy silicon oxide rocks, is a relatively light gas molecule, right?
Exactly. It's much lighter. So instead of sinking, Silane gas can happily remain suspended high up in the brown dwarf's upper atmosphere.
Ah, and that's where JWST could actually see it, because it wasn't hidden deep below.
That's the solution right there. The accident acts like a time capsule. It shows us the default silicon chemistry in a primordial oxygen-poor environment. And this confirms a really deep chemical principle for you. The ultimate fate of silicon in a planet's or brown dwarf's atmosphere, whether it ends up hidden deep inside as rock or floats visibly as a gas like Silane, is dictated by the elemental recipe of the universe at the time and place it formed. Specifically, the amount of available oxygen. It really underlines why studying these outliers, these extreme cases, is so important. As one of the researchers said, sometimes it's the extreme objects that help us understand what's happening in the average ones.
Okay, connecting this to the bigger picture then, this means if you're an astronomer trying to model the atmosphere of some gas giant exoplanet you found, you can't just assume its chemistry will be like Jupiter's, can you? You now have to factor in its likely age, maybe where in the galaxy it formed, to figure out if its silicon is likely hidden or visible as Silane.
That's exactly the implication. This is a fundamental shift for atmospheric modeling. It gives us direct observational proof for those theoretical models of cloud formation and chemical sequestration. The question shifts from if silicon compounds are there to where they are, based on the object's formation history and metallicity.
And studying brown dwarfs helps us figure this out for exoplanets too, right?
Yeah.
Because they're similar atmospherically, but easier to study in some ways.
Yes, they're fantastic laboratories for this kind of work. Because brown dwarfs are usually flying solo, they aren't overwhelmed by the blinding light of a nearby host star, which makes it much easier to get clean spectroscopic data from their atmospheres compared to most exoplanets. We can really test the physics and chemistry in detail.
So figuring out this complicated chemistry on an ancient brown dwarf isn't just about understanding brown dwarfs themselves.
Not at all. It's essential groundwork.
Yeah.
By tackling how these elements behave under these ancient different conditions, we're basically setting up the scientists who are one day going to have to do this kind of chemical analysis for rocky, potentially Earth-like planets.
Because the data we eventually get from those smaller, potentially habitable worlds It's going to be even fainter, even more complex, right? And we'll need this kind of fundamental understanding of atmospheric chemistry, this framework to even begin to interpret what we're seeing and figure out their composition or potential for life.
Absolutely. So the accident, this strange ancient object, really showed us that the missing silicon in places like Jupiter wasn't truly missing. It was just efficiently hidden, sequestered deep down because of the oxygen-rich environment it formed in relatively late in cosmic history. Silicon's there, just deep below our line of sight.
And what really stands out, I think, is this idea that Senilene's presence confirms the atmosphere is like a chemical fossil. It holds a record of the universe's composition at the very moment that world formed. So thinking ahead, we're finding more and more exoplanets and brown dwarfs that are older than our solar system. It makes you wonder, doesn't it? What other crucial chemical fossils, maybe molecules we haven't even thought to look for yet, are floating out there in the atmospheres of these ancient worlds, just waiting to tell us secrets about the earliest chapters of the cosmos?